Welcome back to Fun Facts Online. Today we are stripping away the user interface and looking directly at the silicon heart of the future. There is a clock ticking on a countdown that most of the world cannot see. It is not measured in seconds or minutes, but in qubits and error rates. This is the race to Y2Q, the year a quantum computer becomes powerful enough to shatter the cryptographic foundations of our digital society. For decades, we have relied on the mathematical difficulty of factoring large integers to secure everything from state secrets to your credit card transactions. But these defenses are brittle. They are mathematically destined to fall before the might of Shor's algorithm running on a sufficiently large quantum machine. The solution, as many of you know, is Post-Quantum Cryptography, or PQC. This is a new suite of algorithms designed to withstand the quantum onslaught. But here lies a critical, often overlooked paradox that we are going to dedicate this episode to exploring. Algorithms that are mathematically secure in the abstract world of software can be fatally fragile when instantiated in the physical world of hardware. When a PQC algorithm runs on a silicon chip, it interacts with the physical laws of our universe. It consumes power. It emits electromagnetic radiation. It takes measurable time to execute. These physical byproducts are not just noise, they are leaks. To a sophisticated adversary, the fluctuations in a chip's power consumption during a polynomial multiplication can reveal the secret key just as surely as a mathematical break. So today we are doing a comprehensive technical deep dive into the hardware battleground of the post-quantum era. We will explore the new NIST standards, dissect the unique hardware vulnerabilities they introduce, and examine the cutting-edge engineering defenses, from masking gadgets to lattice-based PUFs, that are being forged to secure the silicon root of trust for the next century. Let's start with the new tools in our arsenal. In August 2024, the National Institute of Standards and Technology, or NIST, finalized the first batch of PQC standards. Unlike the old RSA methods based on number theory, these new champions are largely built on structured lattices and hash functions. The first big name you need to know is ML-KEM, formerly known as Kyber. This is a key encapsulation mechanism. In simple terms, it involves finding a vector of secret numbers that, when multiplied by a public matrix and obscured by small error noise, produces a given result. When we move this to hardware, the heavy lifter is polynomial multiplication. The algorithm operates over a ring of polynomials, requiring thousands of multiplications and additions. The hardware bottleneck here is something called the number theoretic transform, or NTT. Similar to a fast Fourier transform, the NTT allows for rapid polynomial multiplication. But in hardware, this translates to a massive demand for modular arithmetic units and complex memory addressing schemes known as butterfly operations. These operations shuffle data back and forth across the chip. And this shuffling is a prime target for side channel leakage, because the movement of data creates distinctive patterns. Next up is ML-DSA, formerly dilithium. This is a digital signature scheme. It uses a paradigm called fiat shamir with aborts. The signer generates a candidate signature, checks if it leaks information about the secret key or if it is too large, and if so, it aborts and tries again with a new random nonce. This introduces a unique hardware beast called rejection sampling. The non-deterministic nature of rejection sampling is a nightmare for hardware designers. A circuit that loops an unpredictable number of times creates a variable timing signature. If an attacker can correlate the time taken to generate a signature with the secret key, the system is broken. We also have SLH-DSA, formerly SPHINCS+. This is a stateless hash-based signature scheme. It does not rely on lattices. Instead, it uses a massive tree of hashes, specifically Merkle trees, to authenticate a one-time signature key. The hardware profile here is extremely conservative but computationally heavy. A hardware accelerator for this is essentially a massive, parallel hashing engine. The sheer volume of memory access required to traverse the hash trees consumes significant power, making it challenging for energy-constrained IoT devices. Finally, there is fluorine mononitride DSA, or Falcon. This offers the smallest public keys and signatures, but requires high-precision floating-point arithmetic to sample from a Gaussian distribution. Floating-point units are large, expensive, and notoriously leaky in terms of side channels. Implementing constant-time Gaussian sampling on hardware without leaking information via the floating-point unit is one of the hardest challenges in PQC engineering. Now that we understand the algorithms, let's talk about how silicon bleeds secrets. In the classical world, hardware attacks were well understood. In the PQC world, the attack vectors have mutated. First, we have side-channel attacks. This exploits the correlation between physical measurements and internal data. Consider power analysis. When a register on a chip flips from 0 to 1, it consumes a tiny amount of dynamic power. By averaging thousands of traces, an attacker can see the Hamming weight of the data being processed. In PQC, the large polynomial coefficients, which are often 12-bit or 23-bit integers, are much louder than the single bits often analyzed in classical AES encryption. Then there is electromagnetic emanation. Remember those butterfly operations in the NTT I mentioned? They move data across the chip in specific patterns. These physical movements create spatial electromagnetic patterns that can reveal which coefficients are being processed, allowing an attacker to reconstruct the polynomial. Timing attacks are another major threat. PQC algorithms often have conditional branches. For instance, in the decapsulation phase of Kyber, a comparison is made between a re-encrypted ciphertext and the received ciphertext. If this comparison is not perfectly constant time, down to the exact clock cycle, an attacker can deduce the message. Beyond passive listening, there are active attacks known as fault injection. This involves actively disturbing the chip, perhaps by zapping it with a laser, undervolting the power supply, or glitching the clock to cause a specific error. In dilithium's rejection sampling, the hardware loops until it finds a safe signature. A precisely timed voltage glitch can force the loop to exit early, outputting a bad signature that leaks information about the secret key. In Kyber, the decapsulation integrity check is crucial. If an attacker can glitch the instruction pointer to skip this check, they can perform a chosen ciphertext attack on a device that is supposed to be secure, recovering the key with just a few thousand queries. Perhaps the scariest is zeroing memory. In lattice schemes, if an attacker can force the memory storing the error polynomial to 0, the math collapses into a simple linear system that can be solved with Gaussian elimination, instantly revealing the key. So how do we defend the silicon? Defending PQC hardware requires a defense in-depth approach. The gold standard for defeating power analysis is masking. The idea is to split every sensitive variable into multiple random shares. The hardware never operates on the secret directly. It operates on the shares independently. The challenge with PQC is that it relies on arithmetic masking, specifically modular addition, whereas classical crypto used Boolean masking. PQC algorithms constantly switch between Boolean operations for hashing and arithmetic operations for polynomial math. This requires conversion gadgets to switch between masking types. These converters are computationally expensive and are hotspots for leakage. Engineers are developing specialized masking gadgets, like a masked butterfly unit that can perform the NTT operation on split shares without ever recombining them. Another defense is shuffling. If masking is camouflage, shuffling is a shell game. Instead of processing polynomial coefficients in a fixed order, hardware accelerators can use a linear feedback shift register to generate a random permutation of indices. The NTT is computed in a random order every time. An attacker averaging power traces will just see a blur of noise. To defeat timing analysis on rejection sampling, the hardware can be designed to always run for the worst-case number of cycles. If the valid signature is found early, the circuit continues to perform dummy math, burning power until the counter runs out. This flattens the power profile and hides the rejection rate. Against fault injection, we use redundancy and infection. Critical operations, like signature verification, are executed twice. If the results do not match, the hardware locks down. Infective computation goes a step further. Instead of a simple check that says yes or no, the result of the check is mathematically mixed into the output key. If the check fails or is glitched, the output key becomes garbled and mathematically useless to the attacker, rather than revealing the true key. All of this complexity means general-purpose CPUs are becoming too slow and too leaky for high-security PQC. The industry is moving toward dedicated hardware accelerators. The heart of any lattice-based crypto system is the NTT accelerator. Modern designs use a unified butterfly architecture, a logic block configurable to support the slightly different parameters of ML-KEM and ML-DSA. To prevent memory bottlenecks, these accelerators use conflict-free memory banking, ensuring parallel compute units can fetch coefficients simultaneously without stalling. We are also seeing specialized Kakak and SHA-3 engines. Since PQC algorithms use SHA-3 for generating massive pseudorandom matrices, standard cores are insufficient. New accelerators implement full-width sponge functions that can absorb and squeeze data at the maximum rate of the memory bus. Even the open-source RISC-V architecture is adapting. The vector cryptography extension is being tuned for PQC, with new instructions proposed specifically for finite field arithmetic. This allows a modular reduction to happen in a single cycle, rather than 50. These PQC coprocessors are often given their own private, tightly coupled memory to store large intermediate polynomials, keeping them out of reach of other processes and cache timing attacks. A critical application of all this is secure boot. The code that runs when a computer is first turned on, the root of trust, must validate the operating system. If a quantum computer can forge the signature on a malicious update, the device is permanently compromised. A great case study is the Open Titan project. They needed a quantum-secure signature for boot verification. They chose SLH-DSA, the slow, hash-based SPHINCS+ scheme, over the faster dilithium. Why? Because dilithium relies on lattice hardness, a newer assumption. SPHINCS+ rests solely on the security of the hash function. For a read-only memory implementation that cannot be patched, boring security is better than fast security. They accepted the slower boot time in exchange for long-term certainty. We are even seeing the rise of Lattice PUFs, or physical unclonable functions. Instead of storing a secret key, a device uses its own manufacturing variations in the silicon, as the error term in a learning with errors instance. The chip measures its own physical error to reconstruct the key, mathematically binding the post-quantum key directly to the atomic structure of the silicon. As we conclude, it is clear that the transition to PQC is not a flip-the-switch event. We are entering an era of hybrid cryptography. Hardware of the near future will run both classical ECC and Kyber simultaneously. If Kyber breaks, the ECC part protects the data. If quantum computers arrive, Kyber protects the data. We also need hardware agility. Hardwiring algorithms into silicon is risky if standards change. The solution is embedded FPGA technology, where a small patch of reconfigurable logic allows engineers to reprogram the circuit structure itself in the field. The arrival of post-quantum cryptography is the biggest overhaul in digital security history, but the math is only the blueprint. The hardware is the building. As we move toward Y2Q, the focus is shifting from the whiteboard to the clean room. The challenges are immense, masking quadratic lattice operations and stabilizing rejection sampling against glitches. But the defenses are evolving just as fast. The quantum computer may be inevitable, but with robust hardware defenses, the data it seeks to decrypt will remain a ghost in the machine, mathematically accessible but physically out of reach. Thanks for listening to G Fun Facts Online. I will see you in the next deep dive.